This discussion on tipping points is very common on the climate change side, and there is some controversy about it since the models do not actually do tipping points, and people derive heuristically some estimates of how close we are or how fast we are approaching the tipping points and so on. And I'm not a big fan of it since there are so many things to deal with, and adding something so uncertain doesn't necessarily motivate any more action, as we have seen with the record of negotiating for 25 years and emissions still going strong. But it's scientifically interesting nonetheless in terms of where there are tipping points and what are the feedbacks even between the tipping points. But in this socio-economic system, let's say the tipping points are always important because you also have social tipping points that you have to worry about in terms of how people switch into a new state. And sometimes new states are exposed by new technologies, like let's say smartphones came along and now everybody's messaging, texting all the time, and most of the discussions are happening on chat groups, and people are talking while driving and talking while crossing the road on the phone, and so on and so forth. So in this section we focus on a specific element of systems with multiple stable states. So when we say tipping points, it's really about jumping from one stable state to another, but this is also kind of not very robust. How long do you have to be in that state for it to be stable, and how many perturbations or how large a perturbation is allowed for it to be considered stable and to be considered a new state, and so on. They are not scientifically easily answered, right? Nonetheless, we will look at these tipping points and think about how can we explain that systems suddenly change their behavior and change their configuration even. Remember that systems consist of components that are connected via feedbacks. So anytime you say system, these internal connections and feedbacks are very important. That's what makes it a system, right? Those feedbacks, those feedback relations can change. You may lose your hearing, and then it affects your brain and affects how you interact with others. Maybe you learn lip reading better, and so on and so forth. For example, grass can compete with woody shrubs in rangelands when grass has a particular density. When the ratio of grass to woody shrubs crosses a certain threshold, grass cannot compete anymore and woody weeds take over. This threshold in the ratio of grass biomass to woody shrubs is the tipping points, but you don't always know exactly where that tipping point is and how that tipping point itself is changing with warming or change in precipitation and so on, or nutrients, human activities, grazing, etc. We can find tipping points in social systems. So here, ecological systems are not the only systems that have tipping points. We can find tipping points in social systems as well. For example, a peaceful protest flips into a violent riot with mob mentality kicking in. And I have podcasts talking about how you may in fact try to induce tipping points by flipping, by using certain levers to maybe get people to act urgently on climate, let's say, or sustainability, or in sustaining a common. Okay, so we can find tipping points in social systems as well. In his best-selling book, Malcolm Gladwell uses the example of New York subway system. When there is a lot of graffiti on the subway vehicles and trash on the ground, people are more likely to be polluters, or they are not careful about trashing themselves. Trashing the place themselves. In the 1980s, the city government started to clean the subway every day wherever they noticed new trash and graffiti. In a clean subway car, people are less likely to put new graffiti or throw trash on the ground or on the floor of the subway car. The feedback dynamics have changed, and cleaner subways can stimulate cleaner behavior, an example of a positive feedback. These experiments are also done with public toilets, where just having the smell of cleaning agents that makes you feel like it has been cleaned motivates people to be more careful about how they use the bathroom and how dirty they leave it behind when they use it or after they use it, and so on. Peer pressure is also a great social driver, but let's not go there. How do we know we are near a tipping point? This is a critical question, but unfortunately we cannot answer it very well. A tipping point is something we cannot directly observe. It's hidden until we pass it. But if the only way to discover it is to pass it, and the point of discovering it is not pass it, we are in a bit of a quandary. This is the problem I have with tipping point reports on climate change that keep on saying we are closer, we are moving faster towards them, and so on, because they're all based on heuristic arguments, not very quantitative in terms of where the tipping points are and when they will kick in and how fast we are approaching them, and so on. In fact, we only observe certain features of the system that are the indirect result of getting near a tipping point. One feature we can exploit is the fact that near a tipping point, somehow the system is balanced. So natural systems especially are staying in some sort of a balance, like an unstable equilibrium, and a little perturbation may then tip it over into a new state. So we'll see that in a minute. When the system is balanced, very small disturbances persist for a long time. So you can, without tipping into a new state, it will continue to function in that present state, but the perturbations can go on. Imagine a marble on a perfectly flat surface. The tiniest push will make the ball roll for a long time, especially if it's no friction and perfectly flat. Imagine, on the other hand, a bowl with steep sides when the marble resting at the bottom of the bowl. So I'll show this in a minute. If you give the marble a push away from the bottom, it'll return rather quickly and stop moving. Thus, as systems approach tipping points, the rate at which they balance themselves after a small disturbance slows down. This is called critical slowing down, and is one method, albeit an imperfect one, to discover whether a system is nearing a tipping point, which means you should be monitoring them very closely and have a good sense of where the tipping points are in space and time. Discovering when complex social and ecological systems approach tipping points is extremely difficult and remains an active area of research. I'll just add some general points here away, from figures from other books and papers. So this is from this source here, talking about stable equilibrium. So we call it stable because small perturbations don't do much. It tends to roll back to this state, and this one is unstable because even small perturbations will push it into this state or this state. So in the real world, you have to be careful because a large enough perturbation will take it over either here or over into a new state as well. So is this really a stable equilibrium, or is it stable in the context of how big a perturbation it can withstand, which is what we are doing in terms of increasing greenhouse gases and warming and melting glaciers, raising sea levels, and so on. We're pushing the system around, and we don't know where the tipping points are, and we don't know how big increase in greenhouse gases can occur before we go into la la land in terms of glacier loss, which is irreversible in the sense it takes forever to rebuild them, even if we stop global warming and sea level rise and so on. And this is a stable equilibrium state 2, which has a different kind of a well, asymmetry here and so on. So can take potentially larger perturbations because it's in a deeper well and so on. Right? Stability wells are interesting to look at. This is an egg balancing on an edge. How much disturbance will cause the egg to fall and experience a new stable domain, which is basically falling down? If the egg is protected, when it falls, it may not break, otherwise it will go splat and spread, but it is a new stable state in that sense. But here it is stable as long as there is no perturbation, but it is conditionally stable, or what we call it here, unstable equilibrium. So you have to remember these things. But if you look at let's come back to resilience later. I will show some climate data later, and you already know it. So since the Industrial Revolution, we are warming, and we are saying we are going into a irreversible state or a tipping point, but my point is that we don't know that for sure scientifically, so you have to convert it into a risk perception, risk computing problem to say, even if we don't know exactly how close or we are to the tipping point, or how many tipping points there are, or what is the new state will be, what the new state will be, or how fast we are approaching them, and so on. The actions may just depend on what risks we want to avoid, and then it comes to cost-benefit analysis. But in the case of sustaining the commons, which is the focus of this particular set of podcasts, you just want to be sure that you are not tipping a water resource body or a pasture or a forest into a state where it becomes an undesirable state, that you cannot exploit that resource sustainably for what you have been doing when it's in this stable state, as opposed to the new state you may push it into. Alright, so let me leave this here in terms of tipping points, but you can add more to it. For example, if we are in global warming and we stop emitting and we reach a new global mean temperature, then what happens? What the new system will look like? Because in the past, the Earth system has been in different levels of warming. When the dinosaurs were around, the CO2 levels were 3 times what we have now. Temperatures were very warm. Arctic didn't have ice. There was no glacier on Antarctica. The Drake Passage wasn't even open. Isthmus of Panama wasn't closed, and so on and so forth. So we do have multiple stable equilibrium states which are related to plate movements, as well as the feedbacks based on just orbital forcing before the humans started perturbing the greenhouse gases and so on. So when you say we are approaching a tipping point, you have to be aware of also saying not only how close you are, but also what the new state will look like, and whether that will be very harmful or only some will get harmed, and so on. For example, if you warm enough and Siberia tips into a snowless warm place and it becomes very rich agricultural land, then somebody benefits, but somebody else may lose from that level of warming and sea level rise, right? So you can have multiple steady states where winners and losers are created. So you have to be careful about how you are trying to fight against the tipping points, and who is fighting against it, and who will benefit from preventing the tipping over, and so on and so forth. So that's where equity, justice, and inclusiveness and other things come in, which we have to worry about in terms of sustaining the commons as well, right? Okay, so we'll come back and discuss a little bit more about resilience in the next podcast. We may be able to wrap up in a couple of more podcasts. Okay.